All right, this is energy number 2. So we did this Hooke's law lab, and we know that when you make a graph of force versus displacement for a spring, that should come out to be a straight line. So let's see. Looks like we were being asked to make a graph of force versus displacement for this spring. One lab group found that force is equal to 1,000 newtons per meter times x, or delta x we have here. So this right here, that's the slope of this line. The slope of this should be 1,000. Construct a graphical representation of force versus displacement, and the hint here, make the maximum displacement 0.25 meters. The maximum displacement 0.25. So if we're going to go up to a quarter here, 0.25, then that would have to go up by 0.05 by nickels, right? 0.05, 0.10, 0.15, and 0.20. So it's just giving us a hint how to scale it. And then, well, let's see. You could get your calculator, if you need it, to help you with this. 1,000 times 0.05, that moves the decimal place 3. So 1, 2, 3. So this would be 50. Right? And then 0.10, that's 100. 150, 200, 250, right? A quarter of 1,000 is 250. So there's my graph. Graphically determine the amount of energy stored while stretching the spring from 0 to 10 centimeters. So remember, the energy stored is this area. So the energy there would be, I can do it graphically. I could also use the 1/2 kx squared that we have from the notes, but I'll just do it right from this triangle. So that's 1/2 base times height. So let's see, that's 0.05, so is that 5? And energy is measured in joules, capital J. So I think that that's right. Yeah. And might have to go grab my calculator in a minute. Oh, there's one right there. And then here, graphically determine the amount of energy stored while stretching the spring from 15 to 25 centimeters. So that's from here to here. So that's this area here. So if you're going to do it graphically, I think I would break that up into a rectangle and a triangle. So this rectangle is 0.10 wide and 150 high, plus this triangle, which is exactly the same as this, right? So I'm not going to do that again. That triangle here is the same as this triangle. So, and that's 15, so that'd be 20 joules. Do you know how to spell, just in case I forgot to put this in the notes about the units here, joules, it's not that. You've probably seen this in chemistry or something. Joules. Named after some French physicist type person. The graph below was made from data collected during an investigation of the relationship between amounts of two different springs, so kind of like the lab that you did, right? When different forces were applied. Determine the spring constant for each spring. Well, the spring constant is the slope of the force versus position, or stretch, as it's called here. So I just need to find the the slope for each one. So for spring 1, the slope would be, looks like, got any nice points here? Let's use this point here. Of course, it goes through 0, 0, so this point looks like it's at 2, 16. So that slope would be, since this is just the origin, 0, 0, the slope is just 16 over 2, which is 8 units would be newtons per meter. And for spring 2, it's a 16 there. The let's use this point, also goes through 0, 0, so the slope is just 20 newtons over 4 meters, which is 5 newtons per meter. All right. For each spring, compare the amount of force required to stretch the spring to 3 meters. Well, I know that the amount of force is equal to kx. So the force for spring 1 would be equal to its k times that x. So force is going to be newtons, and then the force spring 2, to do the same thing, is going to be its spring constant, which is 5 times 3, which is 15 newtons. The E, on this sheet they're using EL instead of just EE. I'm probably going to do EE all the time. The elastic energy stored in each spring when stretched 3 meters. So the energy stored in the spring, the EE, is equal to 1/2 kx squared. You have that from your notes. So the energy, elastic energy stored in number 1 is 1/2 k times x squared, which is 36 joules. And the energy stored in spring 2 is 1/2 k x squared, which is 22.5 or something. 9 times, yeah. Right. 5, determine the amount that spring 2 needs to be stretched in order to store 24 joules of energy. So that's just kind of going backwards or solving for a different thing there. Determine the amount of the amount of stretch. So that would be 1/2 spring 2 is the one with a spring constant of 5. 1/2 k. I don't know how much stretch, but I know I want it to have 24 joules of energy. So just going to do a little math. 5 times 1/2, that's 2.5. So then 24 divided by 2.5. And then I'm going to take the square root of that because I'm interested in what x is. It's about 3.1. Right. Number 6, the spring below has a constant of 10 newtons per meter. That's my K. If the block is pulled, that's an X there, 0.30 meters horizontally to the right and held motionless, what force does the spring exert back on the block? Well, if it's being held motionless, if we wanted to make a force diagram, of course there's gravity and the normal force. It's not moving in that direction. There's the force pushing it this way, and then if it's motionless, everything's balanced, so the spring force would have to be equal to that in the other direction. So force is equal to kx, right? So there's my k, and this block is being displaced. The x is 0.3, so the force is 3 newtons. Which force is it? Well, it's both of those because they're equal to each other. So that's the pushing force. It's also the spring force back on the block. Right? Number 7, the spring below has a spring constant of 20. And the mu is between the box and the surface is 0.4. And just to remind you, the force of friction is equal to mu times the normal force. All right. The box is pushed to the right, then released. Draw a force diagram for the box above when the spring is stretched, yet the box is stationary. So if the spring is stretched, that means the spring is going to be pulling back on the block, and there's gravitational force, it's a normal force. So if the box is stationary, what is the force that's holding it in place? Well, there's some friction there. So if you don't stretch it too much, there might be enough friction to hold it still, and that does seem to be what's happening according to this description. Box is pushed to the right, then released. Oops. Wait. Yes, box is still stationary. So there's my force diagram. For B, what's the maximum distance that the spring can be stretched from equilibrium before the box begins to slide back? So we know what the coefficient of friction is. It's 0.4. So the friction force would have to be equal to the spring force, and spring force is equal to kx. So I think if we write that out, so friction force is mu times the normal force, and the spring force is kx. So hopefully we know enough information that we can figure this out. So the force of gravity, do I know that? Yes, because did you notice this here, that this is a 1 kilogram block, so the force of gravity is 10 newtons. So that means the normal force also 10 newtons. So let's fill in what we got here. Mu is 0.4. Normal force is 10 newtons. The spring constant is 20. And the x is what I'm looking for. Oh, this is actually this part. Sorry. What's the maximum distance before? Yes. So doing a little bit of math there, I think that we get that x is equal to 0.02 meters, which is 2 centimeters. Let me just multiply those two together, divided by 20. Oh, just kidding. I made a decimal place error. I think it's 0.2 meters. Right, because that would be 4 divided by 20. Yeah. Yep. Just double check that. Okay. Do a pie chart analysis for this situation when the spring is stretched beyond its maximum from part B above so that it slides back and then the box oscillates back and forth until it comes to a stop. Why would it come to a stop? Because of the friction. So let's say it moves from here, then back to here, And let's say that's where the x is 0, and then it goes back to here, position C, and then it goes back to here again, and then it comes to rest there. How about that? How about if we do 4 pi's? A, B, C, D. Why do you think that the letters are in that order? I think it's because of that song. Alright, so here at position A, we've got like the stretch is maxed out, and it's either we're still holding it there, or it's just the very, very instant that it's released, so the velocity is still 0. There, it's all elastic energy. And now it's sliding toward B. B, it's going to have a bunch of kinetic energy. Let's see how much we want to put there. How about if I do this? I'll make it mostly EK, but because of that friction, it's grinding along there, so energy is being dissipated the whole time. I'll put that E dis in there. Now, if energy starts getting dissipated, then that is only going to increase. And if it's at rest at the end, and the spring is not stretched, it's just sitting there, then everything has been dissipated. So here, at C, it's turning around again, so the velocity is 0, right? At those extremes where it turns around or where it's just starting, those are places where the velocity is going to be 0. So I think this looks good. Notice that when it got to the other side, that we started with all this elastic energy, it did not get it all back because of the dissipated energy. It did not make it as far as it was from x equals 0 when it was at position A. Alright, so that's some spring stuff, and we'll use that as a springboard for the rest of our unit on energy.